Okay, so we're going to be talking about and defining calorimetry. I have a balanced chemical equation. The calcium plus water, you actually need 2 water molecules, makes calcium hydroxide and hydrogen gas. Okay? And we're going to be looking at what is the energy change in this chemical reaction. Again, in Chem 20, stoichiometry, we just looked at how much product. Now we're going to look at the energy part of the product. Okay? Before I dive into calorimetry, I want to discuss, well, where is that energy coming from? Okay? And it's coming from change in potential energy of the bonds. If we think of what we have at the beginning, okay, we have a whole bunch of calcium metal bonded to each other. So we're going to have metallic bonds in our calcium, and then we've got water molecules. And from Chem 20 bonding, we have an oxygen in the middle, it's bent into hydrogen. Okay? And we're going to be potentially breaking some of those O to H bonds. Okay? We actually have 2 waters for every calcium unit. Okay? So we have a molecule. Then as a product, we have calcium in a very different form. We have calcium 2+. So some electrons have been lost, and we have a couple hydroxide ions. So the water's been ripped apart, and energy is going to be required in order to rip one of those H's away from the water. Okay? Those H's that get ripped off ultimately come together to form a covalent bond with H bonded to H. Okay? So that delta E that I wrote, that change in energy, is really the change in potential energy between the bonds at the beginning and the bonds at the end. Sometimes there is more energy in the bonds at the end, and sometimes there's less energy in the bonds at the end. Okay? There's less energy at the end, that extra energy has to be spit out into the environment. Okay? If there's more energy in the bonds at the end, that energy has to come from somewhere, and it would have came from the chemical environment around this chemical reaction. Okay? So how we measure that change in potential energy is calorimetry. Okay? So calorimetry is the measure of energy change in an isolated system. Okay? And that's why we use styrofoam cups to get that isolated system. Calorimeter is the device that we make those measurements in. Okay. And I have an example of the typical styrofoam calorimeter down below. Okay. 1 or 2 styrofoam cups, a lid, and a thermometer. Okay. Again, the point of the styrofoam is that isolated system. Okay? And it does, again, an incredibly good job at being an isolated system over very short time frames. Okay? So next we're going to talk about how do we figure out how much energy change there was inside the calorimeter during a chemical reaction. Okay. So energy transfer to the calorimeter, or we can think of that as energy transfer inside the calorimeter. So inside our cups, how much energy change happened in there. Okay. Now what we're going to ultimately relate is if we know that energy change in that calorimeter, which I'm just calling a question mark, the only place that could have come from is the chemical reaction. Okay? That's the point of the isolated system. Okay? So if we can figure out there was a change of 100 joules inside the question mark, inside the calorimeter, which is our question mark, there must have been that 100 joule change in the bonds from the beginning and the end. Okay. Two words that are going to get used a lot are system and surroundings. The system is the chemicals, so the chemical reaction is the system. Okay. Okay. The system is going to be related back to the potential energy. Okay. There's going to be a potential energy change. That energy is going to go to the surroundings. Okay. The surroundings in this unit is often water. It doesn't have to be, but in most of your labs, that's where that energy is going to go, and that's where we're going to measure what we're going to measure the temperature change in. Back in Science 10, you learned how to measure the energy change relative to temperature. Okay. So that was a couple years ago. Okay. And we did this with Q is that energy change. You needed to know the mass of where the heat went. You needed to know the specific heat capacity of whatever material the heat went into, and you needed to know the change in temperature. Okay. This is the main calculation that you're going to do in almost every question in this unit. Okay. This is going to let us go from temperature change in the calorimeter to the energy. Okay. So M is mass of warming substance. Again, often water. So in the calcium plus water reaction on the previous slide, the mass is not the calcium mass. That's one of the chemicals reacting. We want to know the mass of what the thermometer is sticking in, where the heat is going. Okay? And in that example, it would be just the mass of the water. The biggest mistake often made by students is adding all the masses together. Okay? It's just the mass of where the heat is going. C is going to be the specific heat capacity of whatever mass that the heat is going into. And we measure this in joules per gram of the material per degree Celsius of the material. Now on page 3 of the Chem 30 Alberta data booklet, you have all the values for materials that might get tested on exams. And for water, it's 4.19 joules per gram per degree Celsius. That's the value we'll use most of the time. Last, we have delta T, change in temperature. And we're going to do this in degrees Celsius. You could actually do it in degrees Kelvin, or sorry, Kelvin units or degrees Celsius. They are equivalent changes. So this is how we're going to get the energy of the surroundings. We're going to put that together and talk about the surroundings and the system next. Okay. So heat transfer and enthalpy change. Okay. You're about to have introduced to you a new term, the key one in thermodynamics. We're not just going to talk about change in energy like I did introing this slide. Okay. What we care about is the change in enthalpy. So what is enthalpy? Okay. Enthalpy is the total kinetic plus potential energy within a chemical system. Okay. Now, the vast majority of that energy is going to be potential energy. And that's what you see in the Chem 30 material and the textbooks as the simplified version of the definition of enthalpy is just potential energy. Okay? Now you're going to see very little change in kinetic energy between the beginning and the end. It's pretty much all potential, and that's what we'll be measuring. So change in potential from the beginning to end, we're going to call enthalpy. Okay? Now the letter enthalpy starts with an E, and E was already used for energy, so the letter H was chosen to represent enthalpy. Okay. We're never going to actually be able to measure the kinetic and potential energy of of our water and calcium at the beginning, or our calcium hydroxide and hydrogen gas at the end. What we're going to be measuring and what we're going to be caring about is change in enthalpy. If I burn some material, what's the difference between the beginning and the end? That's what we'll be studying. Reactants to products, what is delta E? How much energy was released? How much enthalpy was released? Or how much enthalpy was absorbed? So I always calculate enthalpy in 2 steps. So you're going to have lots of questions where you're going to have to solve for enthalpy change. First step is what we just discussed on the previous slide. Okay. You're going to get the number value of enthalpy from Q equals MC delta T. Okay. You're going to figure out how much energy went into the surroundings. Okay. Okay. And whatever value you calculate, we're going to assume we didn't lose any. Okay. Again, if we calculate 100 joules of energy went into the water from MC delta T, that must have come from the chemicals. Okay. Then we're going to think about the sign. Okay. Is the delta H value positive or negative? Okay. The sign is going to be negative when energy is released. This is what happens most of the time. Okay? All combustion reactions are energy released reactions. The enthalpy change will be negative anytime you burn anything. Okay? The negative is coming from the fact that the products have less energy. Okay? That deficit in energy is what, we feel that deficit coming out as the heat. Okay? These are exothermic reactions. Okay. There aren't a lot, but some reactions have a positive sign. Okay. When this comes from when energy is absorbed. There are some reactions that actually cool down as they go on. Maybe you've seen or purchased a chemical pack, and when you snap 2 chemicals together, the pack gets colder and you could put it on an injury. Okay? That would be a reaction that has a positive change in enthalpy, and it would be an endothermic reaction. So we're going to get the number from Q is MC delta T, and then think, does the surroundings get warmer, negative, or get colder, positive enthalpy change. We're going to do a calculation in a second, but we're going to talk about some of the assumptions you're going to have to use in this course, because we're not always going to have pure water. We may have solutions, dilute aqueous solutions, and how are we going to deal with what if we have 1 molar hydrochloric acid? 1 mole per liter. Well, the solvent is water, but it's not entirely water. Okay? There's a few assumptions that you're going to have to use to solve test questions. Okay? The first assumption has been largely talked about. We're going to assume when we're solving problems that we have an isolated system. Okay? That those styrofoam cups didn't gain or lose any energy from the surroundings. Okay? This is a very good assumption over short amounts of time. If you do a thermochem lab, less than 1% of your error is going to come from heat leaking in or getting out. Okay? The second assumption is that the specific heat capacity of water is constant. Okay, 4.19 joules per gram per degree Celsius. This is the value that's listed in your data booklet, so you do not have to memorize this. This is not perfectly true. When water gets really quite warm, as it approaches boiling, the value changes a bit, okay? But we're not going to factor any of that in. Okay. The second and probably most important assumption that we're going to make is that the specific heat capacity of dilute aqueous solutions are going to be the same as water. Okay. So we're going to use this one in almost every question. If I had 0.10 moles per liter of hydrochloric acid, okay, that means we've 0.1 moles of HCl in a liter of water. Okay. Okay. That hydrochloric acid aqueous is mostly water. Okay. And we're going to use the same value we would for water for that hydrochloric acid solution. Okay. On the same theme of how do we deal with dilute aqueous solutions, okay, if we have a dilute aqueous solution, we're going to treat its density to be the same as water. Okay. What's really handy with pure water is that if you have 100.1 grams of water, okay, because its density is 1.0 grams per mil, 100.1 grams of water is exactly 100.1 milliliters, or vice versa. Okay. In many cases, we're going to measure the volume of water and determine its mass from this 1-to-1 ratio. Okay. But we're going to do the same thing with dilute aqueous solutions. If we had 100.1 grams of HCl aqueous, okay, we're going to use that 1-to-1 ratio and assume it's 100.1 mils. Okay. The more concentrated the aqueous solution, the more this becomes slightly problematic, but all your test questions, you're going to use this assumption. Okay. And in your first lab in this course, you'll mix a dilute acid and a dilute base, okay, and you'll assume both of these last two assumptions. Okay. So let's take a look at a question where you have to solve for enthalpy change. Okay. In a lot of the questions you're going to get in thermochemistry, you're going to have all the whole bunch of data, and then the question is actually buried at the very end. So determine the enthalpy change that occurs in the chemical system above. Okay. So we're asked to solve for delta H. Okay. Our technique to solve for delta H is to do MC delta T for whatever the surroundings is. So now I'm going to read the question and start trying to get some of the key information. Okay, when 50 mils of 1 mole per liter hydrochloric acid is neutralized with 75 mils of 1 molar sodium hydroxide in a polystyrene cup calorimeter, we have a certain temperature change. Okay. So we have two solutions. Okay. Same as in chemistry 20, anytime you're told you have a solution and you're not told what the solvent is, you're to assume that is water. Okay. So this is our calculation for the surroundings, and this is what it is. Most of the time in this course, it is going to be water. So we need to figure out the mass of water, the C value of water we'll just look up, and then we need the change in temperature that occurred in the water. Okay? It's very important we're focused on the water part. First, so how much water do we have? Well, I've got 50 mils of hydrochloric acid, and I'm going to assume any of these solutions, we're going to assume that that is pretty much all water. So we got 50 mils there, but we also have another 75 mils of sodium hydroxide, which is going to be mostly water. So we've got water coming from two places, so I have to add that up. So I have 75 milliliters and 50 milliliters. So I have a total of 125 milliliters. Okay. If one of those were a solid, I would not add it. It's just because it's water-based. Okay. Now I actually need mass of water. And this is something I rarely write down. I'm not going to do it here. 125 milliliters is going to be 125 grams of water, because the density of water is 1 mil is 1 gram. And dilute solutions we're going to treat the same way. Okay. So we have 125 grams of water. We need the C value, 4.19 joules per gram per degree Celsius. That's from your data booklet. Last, we need the temperature change. Okay. Now, I always put in the positive value of the temperature change, the way I solve enthalpy, and then I think of the sign afterwards. Okay. I find that the best method. Okay. So what is our difference in temperature? 25.6 is our bigger number, minus 20.2. That leads to a difference of 5.4 degrees Celsius is our change in temperature. Okay. So we can now solve for how many joules went into the water in our calorimeter. Grams cancel grams, degrees Celsius cancels degrees Celsius, so we are left with just joules. Okay. And our first number, 125, has 3 significant figures. We have 3 significant figures from our data booklet, but we only have 2 significant figures in our temperature. So I'm going to keep the lower one, which is 2 sig figs. So 2,800 joules is what I'm going to round that to. Now, you're going to see me do a lot of conversions. We're going to use kilojoules a lot, which is 1,000 joules. So this would be 2.8 kilojoules if I converted that joules. Okay. But we're always going to get joules first. So that is the number part of our answer. The change in enthalpy number is 2.8 kilojoules. I just need to think of the sign. Okay. Did we get hotter or colder? Did the water get hotter or colder? Okay. The final temperature is warmer. Okay. So this is an exothermic reaction that spit heat out. The chemicals lost heat and the water gained the heat. So I need to put a negative. Okay. The change in enthalpy is negative 2.8 kilojoules, or a release. It's not really a negative. It is a direction. There's really no such thing as negative energy. Okay. So it'd be like antimatter or anti-energy, but you can have it as a sign. It is energy out, and I really want to pound home that notion that the plus and the minus in this unit are either out or in. Positive is energy into the chemicals, minus is energy out from the chemicals. Okay. Last slide before you're going to practice. A chemical potential energy diagram really shows this out and in, and we're going to come back to these a lot later, but I want to intro them right now. Okay. In the example we just did, we're going to look at potential energy, which is a proxy for our change in enthalpy. We're going to see the change in, we're going to see that from beginning to end versus time. So we never measured it, but our HCl and our NaOH had to be at some enthalpy. What we measured was the difference between the beginning and the end. Okay. We just found out that at the end, the enthalpy change was 2.8 lower than where we started. So our products are lower. Okay. So this would be a neutralization or a double replacement. So we're going to get water and sodium chloride. Okay. And again, the reason I put the products lower on this diagram is because of that minus. The difference between where we started and where we finished is 2.8 kilojoules. Okay? I went down because of the minus. Okay? The loss of potential energy. Okay? Okay? So if we think of our bonds, our chemical bonds, there's more potential energy in those bonds at the beginning. At the end, there's less potential energy. And that difference, that 2.8, went into the water, and we measured it.